Good day. What we're going to talk about today is radiation heat transfer. It's the third major mechanism, heat transfer. And we'll go ahead and just give a little bit of physics background for it. It's defined as the transmission of energy by electromagnetic waves or photons. Now it just turns out that all matter emits and absorbs radiation if its surface is greater than 0 degrees Kelvin. So essentially all matter is releasing and absorbing radiation all the time. Now the spectrum of this radiation depends on temperature. And this is a graph of what's called the emissive power versus wavelength. And you can see how temperature dependent that emissive power is. The units of emissive power are watts per square meter per micron, and that's basically just looking at a little narrow window which will integrate out. In the visible, the radiation is between 0.4 and 0.7 microns. Thermal radiation is defined from 0.1 all the way to 100, and that's what we're primarily concerned about in heat transfer. And the microwave, just as a reference, would be 100 and higher, so it's very, very, very low energy. Now, the thing to keep in mind is that this radiant energy occurs at all wavelengths, and you notice how the peak shifts to longer wavelengths as the temperature decreases, and we'll end up getting an equation for that. Now, this is the phenomena of radiation has been the subject of a lot of physicists' investigations, and there are two major ones, Max Planck and Albert Einstein, both of whom you've heard of before. And the part that I think is confusing for an engineer is depending on the measurement you're making, radiation has properties both of a wave and a particle. So what did Planck do? Planck came up with this Planck blackbody radiation equation, which we'll integrate to use. And it has some really interesting constants. Planck's constant, speed of light, and Boltzmann's constant, who was another famous physicist. Where is this function a maximum? If you differentiate it, set it equal to 0, you'll find out that the lambda t is a constant, and that's about 3,000 microns Kelvin. So if you have a surface that's about 6,000 degrees Kelvin, you'll have a maximum temperature at around, maximum wavelength at about half a micron. Now, let's integrate this equation out, and when you do, it takes about 3 pages of math, and if any of you are interested in seeing it, I can share that with you. It's a homework problem for physics graduate students. What will happen is you'll end up with a fairly simple expression for the emissive power as a function of temperature to the fourth. And the constant is called the Stefan-Boltzmann constant, and it's 5.67 times 10 to the minus 8, so it's pretty easy to remember. Now, one of the things that engineers will do with this overall equation is find the emissive emitted radiation from this black body between two wavelengths. And that will then be equal to the wavelength, the emissive power underneath the curve to one wavelength. This is lambda 2, which we can't see, and minus lambda 1. And when you go ahead and do the math, you'll find out that the complex integral gets reduced a bit because you've got this product, lambda t, in the integral. And when people have solved that, then you end up with just a simple curve for the fraction of radiation from 0 to the wavelength of interest. It's just as a function of lambda t. And there are values in the textbook for these band emission values. Now, let's get on to real surface radiation. And there are 4 really parameters we'll look at: emissivity, and then later we'll look at absorption, reflection, and transmission. The emissivity is defined as the ratio of the actual emission from a surface divided by the maximum possible, which would be the black body Planck radiation. And then what you can do, and this is how we use it as engineers, is the actual radiation will be equal to the emissivity, which is usually given, times sigma t to the fourth. So it's a fairly simple expression. Just to give you a physical sense of the emissivity, if you have a metal, it's about 0.1. If you have a non-metal, it's about 0.9. And then the back of the book just has tons of other values that, for individual surfaces if you need another decimal point of accuracy. We have band emission models, so where the emissivity as a function of wavelength is fairly complex. We'll just approximate that with the staircase, and then we'll use basically our F factors to go ahead and compute the average essentially over that wavelength here. Now, if a surface is diffuse, that means its emissivity is independent of direction, and that's primarily the assumption we make with most of our problems here. And then we simplify things further by assuming the emissivity is independent of wavelength, and that's called a gray surface. The other parameters we look at are the absorption, reflection, and transmission of radiation. And here what we do is we look at the incident radiation with the symbol G. Again, emitted radiation is with the symbol capital E. So the reflectivity is the ratio of the incident radiation that's reflected relative to the total incident radiation. Transmissivity, again, total radiation transmitted through an object relative to the total, and the same for absorptivity. Now, of the total radiation coming in, it either gets absorbed, reflected, or transmitted, so that's all equal to 1. As the surface is opaque, transmissivity is 0, and so what we can do, the radiation is either reflected or it's absorbed. Now, another physicist, Kirchhoff, did a very fascinating thought experiment, and it's, I think, talked about nicely in the text. And it turns out that if the radiation is diffuse at a given wavelength, its absorptivity is equal to its emissivity. And I think about it in terms of a baseball analogy. The ability to catch something is the same as the ability to throw it. Now that's just at a particular wavelength. When we go ahead and look at the integral, then there's a consideration as to where the incident radiation came from. And here's basically just a simple example of that. If we have a surface 1 at temperature T1, that will send out radiation which will have a certain spectrum. If it's high temperature, it's here. If it's low temperature, it's here. Now let's look at surface 2. It has a certain absorptivity that's just a function of its own properties. And let's say it has absorptivity where it's 0.8 initially, and then the absorptivity just drops down to 0.2. Now, if we have hot radiation coming on to the surface, that overall integrated absorptivity will actually be closer to 0.8. If we have cold radiation coming onto the surface, then that overall absorptivity will be closer to 0.2. And we can also use essentially the staircase factors like we did earlier to get the overall absorptivity if we know alpha 1 and alpha 2 and the wavelength at which they break. So that's just a very, very quick introduction to some of the science behind the radiation. And what we'll do next with the next talk is actually look at how the radiation within an enclosure behaves. And then there's more engineering in there. So again, look at the book, because I've just taken a lot of this from the book parts. Thank you. Bye.